All right, folks, how you doing today? Today I'm gonna be out. I forgot to mention that to you yesterday. I've got a meeting over at District, so I was actually here today, but I'm just missing your class period. So I'm gonna go over quickly what we're learning today, so we can stay caught up with the other classes. So the first thing you need to do is pause this video right here and copy down everything you see to get us started. So take a quick pause and copy down everything you see. Okay, I'm going to assume you're back with us now. Make sure you have everything copied down with the same variables. I tried to kind of color code this for you, but here's basically what we're looking at. We have a big triangle here that we started with, triangle ABC, and what we did is we drew an altitude here. Altitude, remember, is that line that creates the 90-degree angle here. So that altitude actually created three triangles now. So we have a big triangle, a medium triangle, and a small triangle. So here are the three triangles created by the altitude. And we've seen from a previous lesson that all three of these triangles are similar. So we're going to use that idea that they're similar, using similarity, to prove why the Pythagorean theorem works. So what we're going to do here is we're going to come up with some ratios on the left side of our paper and substitute that in to the right side, to the Pythagorean theorem. We're going to prove that it works. Okay, the first thing I want to try to find a ratio for is A. So I'm going to say A over C on this triangle here, that's long to hypotenuse. A over C on that triangle would have to equal y over A on this triangle, because that's also y over hypotenuse. Now something interesting happens here. When we cross multiply, we end up with A squared equals YC. A squared equals YC means we can replace A squared here with YC. So that's going to be my first step. I replace that A squared with YC. Those are equal. All right, let's try to do the same thing for B. I could say B over C, which would be short to hypotenuse, would be the same as X over B, which is also short to hypotenuse over here. So short to hypotenuse equals short to hypotenuse, just like we've seen before. All right, we're going to cross multiply again, and a similar thing happens. We have B squared equals XC. Okay? So now, if you look at our equation on the right, we've kind of replaced every variable from our original except for C. So we want to have a different way of looking at C. Let's try to relate C to some other variables. So if you look back at our original triangle here, you'll notice C is the entire length, and C is the same as X plus Y, because X and Y make up that C length. So I could say that C equals X plus Y. So watch what we're going to do now. We're going to replace the C with X plus Y. So instead of Y times C, we can say Y times X plus Y. And instead of X times C, we're going to say X times X plus Y. And now we're going to say X plus Y squared. Okay, now this may look like we've complicated it even more, but what we're hoping for is if everything on the left comes out the same as everything on the right, then we've proven by similarity that the Pythagorean theorem works. So we're going to say yx plus y squared, I'm just distributing here, plus x squared plus, I'm going to keep it as xy, or sorry, as yx to keep it consistent. Okay, now when we multiply this out, it's really like x plus y times x plus y, so we have to use the box method or the FOIL method, whichever way you've learned it. So it's going to be x squared plus 2yx plus y squared. Okay, again, it doesn't look like we're the same. It doesn't look like we're the same until we combine some like terms. Combine those like terms. On the right, you have x squared plus y squared, and you have 2yx. And that's exactly what you have on the right side. I just rearranged it a little bit, 2yx. So with that as our conclusion, that's a second way you can prove that the Pythagorean theorem is true, this time just using substitution and similarity. Okay, let's move into another part of our packet here. And again, pause this video if I'm ever going too fast. I'm trying to get through things quickly for you, but feel free to pause it. So our essential question today, we've kind of just answered, is how can similarity help us prove why the Pythagorean theorem works? So let's move into the rest of our packet here. And actually what you're going to find is similarity can help us in a lot of ways. Like if you did this here, if you solve for number 1, it says you have a right triangle, the short leg is 50, the long leg is 100. You could solve for the hypotenuse, I'm sure, by doing 50 squared plus 100 squared equals c squared. Now that's going to kind of take a long time, but you'll get to the right answer. Let's see, what will you get? You'll get 50 squared would be 2,500 plus 100 squared would be 10,000. So then you end up with 12,500 equals c squared, right? So far we're just using the Pythagorean theorem. The drag of this problem is that it just kind of gives you a large number. So we're going to have to break down that into a smaller number. So let's try 125 times 100. That's 10 and 10. And then we have 25 times 5. And that's 5 and 5. So we end up with 5 times 10 on the outside times 5 on the inside, 50 radical 5. Okay, if you're okay with that, not really a big deal. But there's actually a simpler way to do this. And we can use what we know about similarity to help us. So I'm going to start thinking about this original triangle, but watch what I'm going to do. I'm going to just draw a scaled version of it where this side is still half the length of that side. I just use way smaller numbers. So instead of using 50 and 100, I use 1 and 2. So my scale factor here I could think of as like 50. So my scale factor is 50. I made it smaller. So now I can use Pythagorean theorem. So now I have 1 squared plus 2 squared equals c squared. And man, these numbers are a lot easier to work with now. So I end up with c squared equals 5. So c equals radical 5. And now all I have to do is remember my scale factor. Since I made this 50 times smaller, I'm now going to make it 50 times bigger. So my answer would be 50 radical 5, which is the same thing we got up here, just with way easier numbers to work with. It's a faster method. Okay, you can try that out on number 3 yourself. So pause the video here and go ahead and try that method out on number 3. Okay, let's say we're back here. You've tried that out on number 3. I actually only want you to do number 3, number 4, and number 6 on this next little series of pages on the packet. So number 3, number 4, and number 6. Okay, so pause the video again here. Should take you about 5 minutes to do those 3 problems. Should take you about 5 minutes. So go ahead, pause the video again, and take 5 minutes to solve them. Okay, if you're back now from being paused, let's talk about this word problem. I don't have time to go through all of these, but the word problem in particular. So whenever it's a word problem, we want to give our answer in a real number, or an approximation of a real number. So it says we're walking, we went 34 meters to the south. So we started up here at that top dot, 34 meters to the south, and then we turned 42 meters east. Anytime you have a problem like this, there's probably a right triangle somewhere. So you can see it. And now be careful here. What they're asking is how many meters would we have saved if we were walking through the pond. So the pond is here. We want to know is how many meters would we have saved if we had walked through the pond. So how many meters did we walk originally? 34 plus 72, or plus 42. So that's 76 meters is how much we've walked originally. Let's figure out the hypotenuse, and then we'll figure out if we could have saved some time. So 34 squared plus 42 squared equals c squared. So we're going to need our calculator here. So 34 squared is 1156 plus 42 squared equals 1764. So we're going to add those two together, and you end up with 2,920. Take the square root of it. And now here, I know your instinct is probably like you want to simplify that into a radical. But because they're asking for a real answer, let's actually just use our calculator to take the square root of it. So if we back up a little bit, we've got 2,000. We have the square root of 2,920. And it gives you approximately 54. Approximately. It's 54.03. But we'll round to the nearest tenth, so we'll say 54. Okay, how many meters did we save? This is us if we could walk through the pond. This is us what we actually walked. If you subtract these, we saved 22 meters. All right? So a lot of word problems like to use the Pythagorean theorem. Keep that in mind. Here I don't have time to go over it, but it's radical 2. And then on this back page number 6, is this a right triangle? If it's a right triangle, that means that the Pythagorean theorem will work. So let's test the Pythagorean theorem. We know that radical 8 is going to be our C value because that's the biggest number that we're given to test. So we're going to say radical 5 plus radical 3, squaring both of those if it equals radical 8 squared. And remember, what happens when you square a radical? The radicand just is left alone. The radical and the square cancel each other. So 3 plus 5 equals 8, and that statement is true. So yes, this is a right triangle. We can put our little right triangle right there, making radical 8 the hypotenuse. Okay, so that's kind of a mix of review, understanding how to use similarity. What I'm going to introduce to you next is kind of the main idea of where we're going next. So we're going to learn about a special case of triangles. So I'm going to do this first section here, number 4, and all its parts, and then you'll do number 5, and you'll turn that in at the end of class, okay? So number 4. First of all, let's take a look at this. Read through it. We've got an equilateral triangle, so that's important. That means all the sides are the same, so we know that the sides are 2. So then we also know that this whole side here would also be 2. And then if it's an equilateral triangle, they didn't even really have to put this here. These are going to be 60. That angle 60 and that angle 60. Okay. And then also there's this altitude that's drawn here. And when you draw an altitude in an equilateral triangle, what you're actually doing is you're making 2 congruent triangles. So that's our first question. Are these 2 triangles congruent? We could say yes, for sure they're congruent, because of the AAS pattern. So we have angle, angle, side here, and then there's another 90-degree angle there. So angle, angle, side there. So we know they're congruent because of the AAS pattern. So that's the first place to start. Now, second place, they want to know what's the length of the shorter leg. So they want to know like this value here. So because the triangles are congruent, we know they're equal to each other. And because this equilateral triangle is symmetrical, the altitude cut it exactly in half. So what's half of 2 is going to be 1. So our smaller triangle here, the smaller leg is 1. Okay, so it equals 1. Now they want us to use the Pythagorean theorem to determine the length of the altitude. Let's call that x. So we have a right triangle here. I'm just going to pull out the right triangle that we're looking at. We know the short leg is 1, the hypotenuse is 2. We want to know what the altitude is. So we use the Pythagorean theorem. 1 squared plus x squared equals 2 squared. 1 plus x squared equals 4. Subtract 1, x squared equals 3. So x equals the square root of 3. Okay? So the altitude is the square root of 3. Now from here, we've got a bunch of ratios that they want us to set up. So all we're doing is we're going to think about this triangle here, but now we know that the x value is radical 3. So let's think of the short leg to the hypotenuse. That's going to be 1 over 2. Then we're going to think of the long leg to the hypotenuse. That's going to be radical 3 over 2. And then we're going to think of the short leg to the long leg. And that's going to be, let's double check it just to make sure, that's going to be 1 over radical 3. And usually we don't like the radical in the denominator, but since we're just setting up the ratio, we're going to leave it. Okay. Letter G is probably the most important part. Because of AA, all triangles with a 30, 60, 90 degree will be similar. And now, if we draw that same triangle we were looking at from before, that right angle is ugly. We knew that was 60, we knew that was 90, so this must be 30. So if we're looking at that triangle, we know that it has this pattern. 1, radical 3, 2, right? All 30, 60, 90 triangles will have that pattern. So what they ask you here in question G is what if we had a 30, 60, 90 where the hypotenuse was 16 instead of 2? How could we figure out the shorter leg and the longer leg? So we have 2 unknown values here. We want to know that and that. So I'm going to call them x and y. So there's a couple different ways to do it. You could see this a lot of different ways. You could use the ratios we've used before. So you could say x over 16 short to hypotenuse equals short to hypotenuse equals 1 over 2. And then you could cross multiply it, and you could say 2x equals 16, so x equals 8. Another thing you could have done is you could have noticed that, oh hey, the hypotenuse is always going to be double the short leg. So 16 has to be double x, so x must be 8, which is half of 16. So that's another way to do it. Okay, notice now there's a radical coming from here. So we can do the same thing. We can say y over 16 equals radical 3 over 2. Now this gives us a little more math to do, but it's still all right. We're still going to get the right answer. 2y equals 16 radical 3. Okay, now we got to get that y alone, so we're going to divide by 2. So y equals 8 radical 3, because 16 divided by 2 is 8. Now, you might notice about our two answers, y is just radical 3 times of x. That's always going to be true. The short leg is always just going to be radical 3 times. If you multiply the short leg by radical 3, you get the long leg. So here, our short leg was 8, so our long leg was 8 radical 3, because these always have to be multiplied. Okay? This is known as the 30, 60, 90 triangle pattern, and this is basically the heart of our next lesson, knowing how these work. There's another pattern on the next page. I want you to explore a different type of triangle pattern here. Number 5, just go ahead and do A through D, and this will be what you turn into me at the end of class. Okay? It's a different pattern than the 30, 60, 90. Just so you keep that in mind. You're not doing the same pattern. It's a different pattern. But work through this process and you'll figure it out, okay? You're going to rip this out of your packet and turn it in at the end of class, okay? Carlos, try not to be too loud. Thank you. Bye.